My Cubesat development stack has one big problem. It is still tethered to the ground station. On the desktop, being plugged into my laptop is fine, but in orbit, not so much. Using a USB connection between low Earth orbit and the ground station has a few obvious drawbacks. First, the weight of the cable. About 400 kilometers of USB cable weigh roughly 20 tons. Second, the volume. That much cable fills about a third of a standard shipping container. Third, the cost. More than $500,000 for the cable alone. Compared to a Cubesat, these numbers are ridiculous. A Cubesat weighs a couple of kilos. It's about the size of a fist, and I'm targeting a build cost of around $2,000. And then there's the practicality. To keep this USB cable from wrapping around the Earth, the ground station would need to fly at Mach 20, circling the planet every 90 minutes to stay synchronized with the satellite. Clearly, we need to cut the cord and use a radio for communication. Let's briefly talk about the CubeStack and its communication architecture. Inside the CubeSat, the stack consists of 4 boards: power management, avionics, sensor and science, and communications. Let me know in the comments if you would like a deep dive of these boards. These 4 boards form a distributed computer system. We need a communication bus to exchange time, position, attitude, and science data. We use 2 CAN buses for internal communication. The communication board has 2 external links: a satellite modem for photos, videos, and firmware updates, and a packet radio for telemetry, command, and control. The ground station connects through the internet to the satellite modem and uses a second USB-connected communication board acting as a packet radio modem. All these links demand a solid architecture. Thankfully, we can build on the OSI network stack. We need ground station to satellite communication, session management for request-response services, schemas defining how messages and data are encoded, transport libraries that chunk, reassemble, and validate data, routing so that only the right nodes receive the right messages, and finally drivers that move data to and from the wire. Previously, we built a basic packet radio to exchange short messages, but now we need much more than that. Rather than reinventing the wheels, we build on OpenCyphal, an open data standard with documentation, tools, and software libraries for unmanned vehicles, drones, satellites, and more. With OpenCyphal handling the messy middle layers, we can focus on applications and session management, defining messages, services, and architecture, while writing only the low-level device drivers ourselves. Here's the current wired workflow. A USB or UART interrupt stores incoming data frames in a circular buffer. Periodically, we stream frames from the buffer into the OpenCyphal reassembler. The reassembler reconstructs messages and places them on a queue from where tasks and processors pull the messages they've registered for. It turns out we can reuse this entire workflow if we insert a packet accumulator that groups raw packets into frames. A packet is just up to 61 raw bytes. A frame is up to 255 bytes long, starts and ends with zeros, and includes source, destination, message type, sequence number, and the payload, which is the actual message. With this frame accumulator and the radio drivers we built earlier, we can replace the USB or UART serial input with our packet radio. Interestingly, our USB or UART workflow only worked by luck. There's no guarantee that incoming data naturally form clean frames. The DMA-based USB reads happen to skip small pauses without merging frames. But when we switched to synchronous USB reads, frames shattered into fragments, and that broke the reassembler. So we added a frame accumulator to the USB path as well. Better safe than sorry. On the transmit side, tasks generate messages, request services, and respond to service calls. The OpenCyphal serializer turns messages into frames, fills headers, and queues them up. The queue is periodically drained into the USB driver. And again, the same workflow works for radio if we add a packager that splits 255-byte frames into packets of less than 61 bytes. To keep packet sizes as uniform as possible, we shoot for 51-byte packets. These packets go into a packet queue and are periodically drained into the radio. Since the STM32 Blackpill is hardware and software compatible with our CubeStack, we use it as a stand-in communication board. I am connecting power and the transmit and receive pins from a USB to UART converter. Looking at the Yakut display, node 41 sends heartbeats and responds to name, ID and version requests. Switching to radio, the only cable connected to the node is power, yet Yakut shows the same heartbeats and responses, now delivered wirelessly. And here's the SDR view, where we can see the radio packets from both the ground station and the communication board. The stronger packets are from the CubeStack, while the weaker packets are from the radio modem. So we succeeded, we cut the cords. Our CubeStack will be able to communicate by radio. Thanks for joining me at 4111 Spyglass. See you next week.